In today's lesson, we're going to be moving on from one variable analysis to two variable analysis. So we're going to be looking at analyzing two variables, and we're going to first look at analyzing this through linear correlation. So linear correlation is basically just a fancy way of just saying, I want to create a line of best fit. And we're going to look at how we can do that using technology. So correlation is basically used to analyze the relationship between two variables. And what we do is we create a linear model through a process called linear regression. Now, basically, it kind of takes an average and it kind of figures out how far each point is from the average. But basically, as long as you're familiar with the terms, we're going to get technology to do this for us. Now, there are different models that you could make. You could try to see if your model represents a quadratic kind of model or formula, or an exponential, or things like that. We're going to focus only on linear models or line of best fits for our data in this course. And what we're looking for is we're looking for the correlation, again, which is the extent to which two variables are related to each other. So we're basically seeing, are my two variables related to each other? Do these two things have any relation? Is there a relationship here? One thing to keep in mind, correlation does not mean causation. And we'll touch on this a bit later in our next lesson, but this is one thing just to keep in mind. Just because things are correlated or we do see a relationship, it doesn't mean that one causes the other. And we'll talk a bit about that in our next lesson. But what we want to do first is we just want to get right into it and create a scatter plot and linear regression for the following data. So what this is looking for is looking at the weekly income for an Aboriginal population and non-Aboriginal populations over the years from 2007 to 2016. So what we're going to do is we're going to enter the data into our Google Sheets. We're going to highlight the data, we're going to select a scatter plot, and then basically there's an option to select a trend line, and from there that basically does it for us. The technology does it for us, so there's nothing really to it other than just entering our data and then just analyzing it. So I've already entered all of my data into Google Sheets. We have the years, we have the looking at Aboriginal population, their weekly income, and the non-Aboriginal population weekly income. So I'm going to highlight my data. I'm going to go Insert, Chart. Now again, it may come up with something different, but that's okay because we know how to customize this. So I'm going to change my chart type. I'm going to scroll down to Scatter Chart. We can already see it represented here. And I'm going to go over to Customize. So under customizing, I can change some things a bit just to make things a little bit easier. So the title is fine, or sorry, the horizontal axis, no. So I had my weekly Aboriginal income as my X, vertical, weekly non-Aboriginal income as my Y. Now again, we've talked about before, hopefully you at least are familiar with independent and dependent, your X and your Y. So in this case, we're basically saying that the non-Aboriginal income is affected by the Aboriginal income. It doesn't really matter which one you put where, at least in this case, because we might not have any idea of which one influences the other. We just want to see, is there a relationship? We'll worry about if one causes the other later. So it doesn't really matter. You may already have an idea or have already made the decision on which is which. But if not, that's okay. We can worry about that later. I'm going to go to my vertical axis. And again, I'm going to adjust the minimum to kind of bring this all down a bit, to zoom in a bit. So I'm going to bring it down to at least, let's say 700 as my minimum value, just to get a better view of the data. In order to get my trend line now, I need to go down to Series, And if I scroll down, I see a box that says trend line. And there's going to be, in any form of technology that you use, whether it's this, whether it's GeoGebra, whether it is Excel, there should be an option to add a trend line or a line of best fit. So I'm going to click on that, and I can see right away it creates a trend line. So this line or line of best fit is going to be the model of our data. So this is what is going to model or represent our data. If I scroll down, I want to show the label. So label use equation, because I want to see what the equation is. I want to see what linear equation is going to be used to model my data. As well, I want to show the r squared value. So the r squared value pops up here. I want to see that because that's going to be important later on to determine if there is a relationship. Again, I can play around with different customizations in terms of my data. But again, the type, this is going to be the type of model. I want it to be linear. We can see all the different types of possible models that we come up with. Right? We could try to represent it as an exponential, a logarithmic, a polynomial. Right? So there's many different ways or different models that we could use, but we're going to stick with linear in our case, because we're going to stick with the basic as one increases, the other increases, or something along those lines. And that is our scatter plot with our trend line or our linear regression. So once we've created that, there are a couple things that we need to look at. And the main thing is the equation of a line, because that's the whole thing, or that's the whole reason why we're creating the scatter plot and doing the linear regression, is to get this equation of the line. And again, hopefully you remember this all the way back from grade 9, but the equation of a line is y equals mx plus b. Y represents the dependent or response variable, x represents the independent or predictor variable, m is the slope, or basically a measure of increase/decrease of the dependent variable for 1 unit change in the independent. And b represents our y-intercept, the value of the dependent variable when the independent is 0. So again, bringing you all the way back to grade 9, y equals mx plus b. This is what we're looking for when we get our linear regression. So in example 2, I want to interpret the slope and the y-intercept of the linear model from example 1. So I've wrote it down from my graph, and again, that's why we want to again create that label to get that equation so we can clearly see it on our graph. Oops. So we can see it up here. Again, that's why we use equation for a label to get that specific equation. So right from here. Again, it's assuming the y equals 0.923 times x, or x plus 169. So that's where we get our equation from, or that's where I got this value from. So the two things we want to pick out are our slope and our y-intercept. And I want to interpret these values and basically, based on our scenario, what we're looking at, what do these values tell us? Well, the slope is 0.923. And that was the dependent variable is going to change by this amount for every 1 change of the independent. So basically what this means is, in our terms, or in our graph, the y value was the non-aboriginal. So weekly, I'll put NH for non-aboriginal income. Increases by $0.923 for every $1 increase in weekly Aboriginal or A income. Because again, change in y over change in x, so the non-aboriginal income is increasing by $0.293 or 92 cents basically for every $1 increase in weekly aboriginal income. So you could argue, based off of this, well, the non-aboriginal or aboriginal population, or the weekly aboriginal income is increasing greater, you could say. You could also, though, if we look at our y-intercept of 169, so the weekly non-aboriginal income is $169 when the weekly aboriginal income is 0. So, a couple things to point out here. For our slopes, you could argue that they're roughly increasing at the same amount, right? 92 cents to $1. Okay, yes, it's off by 8 cents, but you could argue it's close. It's very close. They're increasing by the same amount. However, we can see that when the aboriginal weekly income is 0, the non-aboriginal income is 169. So even though they're increasing at a similar pace over the years, or just increasing as the other increases, so they're staying on par, the non-aboriginal income is starting off at an advantage, right? It's at an increased amount of 169. So yes, they're increasing at the same amount or by the same rate roughly, but one is starting off way ahead of the other. So it's not quite the same, right? You could argue there's equality in terms of the increase, but there's not equity because one is starting off higher than the other. So the two values do give us some insight into our data. The second thing that we get from our linear equation or our linear regression is the correlation coefficient. So this was the R value, and we got part of it in our equation, in our linear regression. But what the correlation coefficient or R value is, it's a measure of how well the line of best fit fits the data. Or basically it's saying how consistent the data is. And we calculate it by taking the square root of the R squared value. So if I go back to my data or my linear regression, I can see the R squared value is 0.698. So I'm going to take the square root of that number to get my R value. So if I take the square root of 0.698, I get 0.835, and that value is going to tell me how well or how strong is the correlation between these two variables. So basically saying, is there a relationship? And one thing to note, because we're taking the square root and our R squared value is always going to be positive, if the slope is negative, then we have to include a negative for our correlation coefficient. So we take the square root and then add a negative. So again, hopefully we're familiar with what a negative and a positive line looks like. And we can see the different terms used to describe the strength of our correlation. Basically, it's broken down into thirds. Anything from 0 to 0.33 is considered weak. From 0.33 to 0.67, it's considered moderate. And then anything between that and 1 is considered strong, with 1 being perfect, whether it's positive 1 for a strong or for a perfect positive correlation, or to negative 1 for a perfect negative correlation. So same values on either side. One's negative, one's positive. Same characteristics in weak, moderate, or strong. And again, it tells us how strong is there a relationship between it. So in our case, 0.835, positive because it was a positive line. We could argue that this is a strong positive linear correlation between these two variables. So we could argue that there is a relationship or there is something going on between these two variables, the weekly non-aboriginal income and the weekly aboriginal income. There is some sort of relationship or correlation there. We've seen it in the data. We can also use the linear model to predict. And there's two types of predictions. One is interpolation, and this is predicting values that lie within the domain or the range of the values of our data set. And extrapolation is predicting values that lie outside the domain and range of our data. So these are values that we have to consider when looking at, or these are terms we have to consider when making predictions. And the one thing we have to keep in mind, if we're making an extrapolation or predicting outside the domain or range of our data, we need to make the disclaimer if the model continues this way. And the reason we have to state that is because we don't have data that shows that it continues that way. And we just want to make that disclaimer again. It could, and we're making this prediction as if it did. But until we get data or we collect data that shows us that it continues, we have to make that kind of just assumption that we're assuming it continues, but it may not. So what we're going to do now is we're going to kind of use our equation to predict. So you determine the weekly non-aboriginal income y if the weekly aboriginal income x was $750. So this is just basically taking our equation, the y equals 0.923 x plus 169, and we're subbing in the value that we're given. So we're given that x is $750, and we're trying to determine y. So this is kind of going back to grade 9, sub in a value for x, and solve for y. So 0.923 times 750 plus 169 gives us 861.25. So if the aboriginal income was $750, the non-aboriginal income would be $861.25. We could also do the same thing if we're given the other option or the other way. Determine the weekly aboriginal income x if the weekly non-aboriginal income y was 750. So same idea, just backwards. So still using that same equation, y equals 0.923 x plus 169. We're told our y value is 700, and now I need to solve for x. So I move the 169 over, it becomes subtraction. 700 minus 169 is 531. 9 equals 0.923x. Divide both sides by 0.923. And we get that x is equal to $575 and round it to 30 cents. So that means if the weekly non-aboriginal income was $700, then the weekly aboriginal income would be $575.30 based off of our model, our linear model. So again, that's how we can use the equation to predict. Lastly, what we're going to look at is the effect of individual data points. So individual data points have the option to influence our data either for either on the high end or the low end. Basically, these are outliers. And what we can do is we can use what we call a residual plot that shows the distance, positive or negative, that each point lies from the line. And we can use this to look for outliers. Are there certain points that are very far away from our line? And again, we could use our line of best fit, but we may not be able to really tell how far away they are compared to the other data points. So we're going to create a residual plot just to see if there are any points that are very far away. So to create our residual plot, it is going to be a little bit different in terms of what the steps are. There are going to be a few more steps. But essentially what we want to do is we want to create an extra column that's called model. And we're going to basically use the model of our original scatter plot, or the linear regression. So 0 equals 0.923 multiplied by our x value, which in this, the x value, which is the aboriginal, plus 169, our constant, or our y-intercept, and we get equals to, I don't know why it's italicized, but we get the value that it should equal. So basically this is the value that it should equal. We're slightly above. And we're going to do the same thing, or extend it all the way down. So these are all the values that that our non-aboriginal population should be. Second thing we're going to do is create a column that's called residuals. And again, the residuals are the distance each point is above or below our model or our line of best fit. These lines or these points or values represent what the value should be. So I want to take the first value minus the second value and see how far above or below is my actual point, or basically how close to the model does each point land. You can just drag and drop so we can see that we have some points that are extremely high, extremely low compared to our model, and some that are extremely high compared to our model. What we're going to do next, highlight our two columns, insert chart, already as a scatter plot, which is perfect. I'm going to change the title just to residual plot. And what we can see here now, scroll out a bit. What we can see here now is we can see our 0 is essentially our line of best fit. And then each point is actually what or how far away from that line our data values are. So we can clearly see we have some that are extremely high and extremely low, extremely high and extremely low away from that point, and these ones are kind of clustered around it. So we could argue that these 2 points here, these residual values, these ones are, we could argue, outliers. They don't fit the pattern because they're very far apart. So we could go back if we wanted to, remove them from our data set entirely, including the Aboriginal population one, both entire data sets. So this would be the 62. So I would take out this entire last column as well as negative 53. So I would take out 2013 entirely, because those 2 years I would say are outliers. They don't really fit this general pattern. And this would again represent our residual plot, and again helps us again represent or see how the data is spread out and how well it fits the line of best fit or our model. So just another way to visually represent that, but again primarily to identify the outliers. Because if we look at the two, we can see that it might look like it's close to our line here or not that far off, but when we look at all the points in general, we can see that it is quite a distance for these two. These ones are quite a few values away from what we should get based off of our model. And it is a strong model, so we can argue that the relationship is there. So Again, the main thing that we should get out of this lesson is just how to, one, create a scatter plot for two variables, how to create a linear regression to get us our linear equation or our linear model, how we can use that linear model to describe our data, to describe the possible correlation or the relationship, you getting the correlation coefficient to describe the strength of the relationship, as well as creating a residual plot to just look for any possible outliers. And again, we're using technology, again, just to make it a lot easier, so please make sure we are comfortable with those steps.